right. Thanks, Deanna. I'm excited to introduce Nick Suminski today in his senior experience talk. This is one of the most unusual talks for me to introduce because I met Nick when he was taking my inorganic class several years ago, and he was a very diligent student, got everything done, and did well in his work and everything like that. And then he took my advanced inorganic class later, and the final project for that class is a independent research proposal, which always results in students coming to me with amazing ideas. I love that class. I'm teaching it right now, and it's so intellectually stimulating. I just really enjoy it. But this project that Nick is about to tell us about was a direct result of Nick's proposal in that class, which is a little unusual. I have not taken that step with any other student yet to give them the space to actually try their project that they propose. But I thought the scope of Nick's proposal and the intriguing nature of it was ambitious, but not so ambitious that it wouldn't be potentially achievable in a normal scenario. Now, we are not living in a normal scenario, and I think Nick will probably have to address this in his talk because the time he had to devote to this work was cut short by us all being evacuated out of our labs and into our new spaces here. But I still wanted to say that this is not for lack of trying. So Nick is an incredibly hardworking student. He's one of our double degree students and also a very accomplished piano player. So I think that any one of those accomplishments on their own would be very impressive, but the work you're going to see here in combination with also juggling festivals and all that kind of stuff over the summer really is an impressive tour de force. So Nick, I'm looking forward to hearing what you have to say about your FLPs. The floor is yours.
Okay. Thank you so much for that introduction. Hi, everyone. I'm Nick, and I'm going to be talking to you today about my work in synthesizing flexible Lewis pairs for use in hydrogen evolution catalysts. So probably all of you are wondering, what the heck are we even talking about? So I'm going to start by defining, sort of in very broad strokes, a couple of terms for you. We're going to get into those a little bit more later. But I'd like to start with hydrogen evolution catalysts. These are, as the name suggests, a catalyst. This means that they are some chemical species that makes a reaction go faster. They are not consumed in the reaction, but by adding them, we can make the reaction go faster. And the specific reaction we are talking about is what is called hydrogen evolution. This is when we evolve hydrogen gas by splitting water into its elemental forms. You've probably all heard of dihydrogen monoxide. We can actually take those constituent elements and break them down from water. The other term I would like to define for you is a flexible Lewis pair, and I will get much more into what these are later, but for now what you need to know is that this is a type of molecular switch. This means that it is a molecule that actually changes its shape, its conformation in response to its environment. And we can also think of these as a type of functional group. This is a sort of a preset pattern of atoms bonded together with some kind of chemical function that we can attach to other molecules. And in this case, I'm interested in attaching this functional group onto a hydrogen evolution catalyst. So what's the actual link between these two things that I found and got super interested in? The answer, in short, is platinum. So I basically found that this group led by Nicole Arsenault at the University of British Columbia had recently functionalized a flexible Lewis pair onto a platinum center. Platinum centers are also involved in hydrogen evolution catalysts. So my basic question behind this was, can we use the Arsenault product to evolve hydrogen? So what did I do to find this out? So the first step is I had to synthesize the Arsenault product. This is a new thing. It's not like I can go on the internet and buy it. I have to make it in a lab. And then after that, I wanted to find out if it was active as a hydrogen evolution catalyst. As I will show you later, there are some chemical similarities between the two that I thought showed promise. After that, I wanted to sort of characterize how it went about this. I wanted to collect further characterization data on the molecule itself, and I also wanted to see how its activity changed depending on its conditions as a hydrogen evolution catalyst. And finally, from this information, I wanted to propose new, more efficient catalyst designs so that we can evolve more hydrogen. So where am I actually going to go today? I'm going to start with hydrogen evolution, and I'm going to explain to you why it should change your life, why we care about it, and where we're going with it. After that, I'm going to delve into flexible Lewis pairs. I'm going to explain what they are and how they can actually help us with hydrogen evolution. And finally, I'm going to talk to you about the synthesis that I attempted, what went wrong, why it failed, and what I'm going to try if I ever get to try this again. I also, as Graham mentioned, I wanted to mention to you that this is unfortunately something of a work in progress. I never managed to finish synthesizing my flexible Lewis pair, so much of what I'm going to be talking about is the work that this project was built on, and the sort of progress that I have made and where I intend to go as my next steps. So I'm going to start by talking to you about a dream. This dream is the hydrogen economy. The hydrogen economy describes an economy that is entirely powered by hydrogen fuel. And this is important and exciting because at present, we live in a fossil fuel economy. And right now, we are just burning way too many fossil fuels and releasing way too much CO2 into the environment. And as we all know, this is a major driver of climate change, which is going to have catastrophic implications within the next few decades. So what are the advantages of hydrogen as an alternative to fossil fuels? So the first and maybe most important is that it has a very high energy density by weight. This means that we can bottle it up and haul it around over long distances, which makes it great for using as a fuel in vehicles, among other things. There is no CO2 released in the combustion of hydrogen. The only product of hydrogen combustion is actually water vapor, which is great because we are not contributing to CO2 emissions by combusting this. And finally, we can use it as a renewable energy storage system. This means we can use energy from other sources, such as wind or solar, and we can convert that energy into hydrogen fuel that we can then use to power vehicles and other things. So this is actually an example of a prototype vehicle developed by Toyota, which is powered by a hydrogen fuel cell. This is a way of actually oxidizing hydrogen fuel. It's a slightly different from the traditional combustion engine, but essentially,
Nick,
yes,
your slides aren't changing.
they're not changing.
Mm-hmm.
Where did we get stuck?
We are still on your first slide.
Really?
I thought it was mine because my internet is going in and out, but I've gotten some messages. So maybe try the share again, and maybe it didn't share right, and go back to the one with the bar.
Okay. That is unfortunate. Let's see.
Sorry that my internet's going in and out.
So we want to do the PowerPoint, right?
Mm-hmm.
Can you see it?
I can see this, but try and advance something.
Let me see.
Yes.
It is
now
working.
It's changing.
I love Zoom. Okay. I don't know how far we're going to go back. I think we'd probably better forge on for the sake of time. We've got another talk after this. Well, this is the example of the hydrogen-powered car. Okay. So what's the catch in this whole hydrogen economy dream? We'd love to power our entire economy with hydrogen, but the current method of producing hydrogen that we produce most of the hydrogen in the world with is a method called steam methane reforming. And on the right here, you can see a picture of one of the plants that they use to do this. And there are a few issues with this method. One is that it requires methane, which is a fossil fuel of sorts, and which also contributes itself to global warming. It requires very high temperature cracking in order to produce the hydrogen gas. And finally, this production method actually releases CO2, which is a little bit self-defeating, because if we're trying to make fuels that don't release CO2, it's a little unfortunate if the method that we have to use to produce them releases CO2. So the solution to this is actually direct proton reduction. So we start with some source of protons and we dump electrons on it to make hydrogen gas. And this is sort of what we call a half reaction. It's the reduction half of a redox reaction. The complete reaction that we're looking at is also called water splitting. And this is breaking down water into its elemental forms, one of which is hydrogen. So how do we actually go about doing this? So the more traditional way of doing this is what's called electrolysis. And you can actually do this at home with a 9-volt battery and a glass of water. It helps if you dump a little bit of salt into it. And you can actually see that hydrogen gas is evolved at one terminal of the battery. Now this is cool, but it requires some kind of external power source. And we can do that with renewable energy such as wind or solar energy. But it would be nice if we could produce it all in sort of one sleek system. So the answer to that is photocatalysts. Photocatalysts, this is a ruthenium-containing photocatalyst, and they are catalysts that absorb light energy, specifically light in the UV-vis range, and this excites electrons within the photocatalyst that can be then used in further downstream reactions to produce, in this case, produce hydrogen, although you can actually do a number of reactions with these photocatalysts. So the way we implement these photocatalysts, specifically in hydrogen production, is using what we call the 3-component system. Now, this thing looks very intimidating, but I'm going to break it down for you in much simpler terms. So the goal ultimately is to increase the energy that we are storing in the form of hydrogen gas. So our story starts with an electron in the ruthenium photocatalyst, and by applying light energy to this, we can excite this electron into a higher energy state. Now this light energy can come from a variety of sources, but because it is in the UV-vis range, there's some promise that we could use solar energy for this purpose, which would be very exciting because solar energy is available all over the Earth and is being beamed at us all the time. From there, we use something called methyl viologen, which relays it to another catalyst. And this catalyst we then use to kind of lever the energy from this excited electron into forming hydrogen gas. Now, what my work here focuses on is actually this catalyst, this specific catalyst. And this catalyst usually contains platinum, specifically in the +2 oxidation state. Now, why is platinum really good for use as this kind of catalyst? Platinum-2 tends to form these very flat, square planar structures with electron density above and below. The orbital in which these electrons are is a very good match for proton orbitals, and essentially allows a very good, strong interaction with protons in which the platinum donates electrons into the proton orbital. So we can see this in the platinum catalytic cycle. So if you start at the top, we start with our platinum-2 catalyst. A proton kind of swims in and it binds to this electron density located above and below the platinum. Another proton comes and it binds to that same electron density, actually pulling this electron density away from the platinum. And here we see that H2 is released. We have taken 2 electrons off of our platinum to neutralize the charges on the protons, and hydrogen gas is evolved. From here, we have sort of regenerated our platinum catalyst, but it is in the +4 oxidation state because we ripped 2 electrons out of it. So we go back to our 3-component system, which is shuttling electrons back to this, and we regenerate our catalyst. So what's great about this is that platinum is very, very expensive. So it's nice to be able to do this without actually consuming platinum in the cycle. And as we see, using this system, electrons are shunted back onto the platinum, and we continually restore our catalyst so that it is not actually consumed. This means that a very small amount of platinum can be used to generate a large amount of hydrogen gas. So what's the problem with this platinum catalytic cycle? Well, the big problem is that we know sort of surprisingly little about it. We don't know, in particular, the most important thing is we don't know what the rate limiting step of this catalytic cycle is. And we would like to find the rate limiting step so that we can make sure it limits the rate less. And that way we can produce more hydrogen fuel faster. So how do we design a better catalyst that is more efficient at producing more hydrogen fuel? So this is a paper that I read. I'm sorry this slide's a little bit complicated, but I'm going to walk you through it. And this paper essentially proposed a lot of different platinum catalysts. This one was the one they found was the fastest, but was actually less interesting to me for my purposes. These two in the middle show an interesting trend. What we see is that platinum catalysts which have ligands that are sort of form these loops, ligands that attach to the platinum at two different sites, tend to be slightly more efficient. But the one that actually interested me the most for this project that I'm working on is this one all the way on the right. And the reason is I spotted a structural similarity with something I had seen elsewhere in the literature. So this is just another picture of that, and we can see highlighted in red the part that is similar to what I spotted in the literature. But this thing on the right is from the actual arsenal product. This is what my synthetic target is. And this was what the platinum center that they had functionalized to the flexible Lewis pair. And so I decided what they had not checked with this was whether it actually was capable of generating hydrogen. And so I decided I was going to synthesize this and see if this chemical similarity was close enough that it could actually generate hydrogen fuel. Okay, so now I've talked to you about the basic motivation for what I'm doing here, but you're probably wondering what all this stuff in black is. This stuff in black is what is called a flexible Lewis pair, and I'm going to explain to you what those are. So let's start with sort of the basics of what these are. As I mentioned at the beginning of this talk, this is a type of molecular switch. That means it changes formation in response to its environment. And specifically, what it is reacting to in its environment is changes in solvent and temperature. And alongside these structural changes come electronic changes. We actually see differences in the way the orbitals within the molecule interact. So, backing out even further for 1 second, what is a Lewis pair? A Lewis pair, you are probably all familiar with from the definition of a Lewis acid and a Lewis base that you got in basic chemistry, introductory chemistry, I mean, excuse me. But to walk through it right now, again, what a Lewis base is something with a high energy unpaired electrons, while a Lewis acid, pictured here on the left, is something with a relatively low energy empty orbital. And when you put these together in a pot, the electrons from the Lewis base can actually fill the empty orbital on the acid and form what is called a Lewis adduct. However, if this is too bulky, if the Lewis acid and base are surrounded by large bulky functional groups, they actually can't get close enough to each other to react and form this adduct. And what we call this is a frustrated Lewis pair. So what a flexible Lewis pair is somebody one day thought, wouldn't it be interesting if we could sort of find some in between where it can sometimes form the adduct and sometimes can't? And the way they do this, as we can see, we have a Lewis acid over on this side, a boron, which has an unfilled p orbital. And on this side, we have a Lewis base with an oxygen with a high energy, relatively high energy lone pair. And we have these bulky functional groups, which we would normally think of making this a frustrated Lewis pair. We have very large mesotyl and phenyl groups. However, because these are held in close proximity, because they are actually bound to the same bithiophenol backbone, we see that adduct formation can sometimes still happen. It also helps that this oxygen extends away from these bulky functional groups and allows these to get closer together. And so we see an equilibrium between what we call the open and closed form. And the reason we call it this is here we see a ring. There is a continuous ring of chemical bonds, which is being linked by this dative bond between the adduct, as opposed to the open form, where this ring is actually broken and it is much freer to move. So what factors affect where we lie in this equilibrium? Excuse me. So the main factor that I am interested in is actually solvent. And what we see is that hydrogen bond donating capacity of the solvent is the main factor that influences where we lie in this equilibrium. So what we actually see is that hydrogen bonds compete with the formation of the adduct. They actually draw that unpaired Lewis base electron pair, that Lewis base electron pair, they actually involve in hydrogen bonding, which competes with the formation of the Lewis adduct. We also find that temperature is a factor. I'm going to be talking about that less, but essentially what we find is that the open form is more favored entropically, so the higher the temperature, the more it is in the open form. So what does the solvent effect actually look like? So what we see is if we put this into a hydrogen bond donating solvent, which I have here represented by HX, this could be something like water or ammonia, for example. There is a hydrogen bond interaction that can occur in the open form. So this actually stabilizes the open form of this molecule. Whereas when there is less of a hydrogen bond donating solvent present, this electron pair is more free to interact in this bond. So what evidence do we actually have of this? So I'm going to show you some actual data from this, from some of these papers. So the data we are looking at here is Phosphorus Nmr data. So essentially this tells us how much electron density is concentrated on this phosphorus. So the further we go to the left, the more electron density is being pulled off of the phosphorus, whereas the further we go to the right, the more electron density is concentrated on that atom. So what we have here is a kind of a control molecule. It is chemically similar to a flexible Lewis pair, but it does not contain the boron that we would need for it to actually be a Lewis pair. So essentially they ran phosphorus NMRs of this thing in various solvents, and I've shown you the solvents here at the bottom. They are ordered from left to right in order of how hydrogen bond donating the solvent is. And I've used for that this alpha parameter, which comes from a paper by Camlet and Taft, and it's essentially just a parameter that we can use as a proxy for how strong are the hydrogen bond interactions in that solvent. And what we see is that the stronger the hydrogen bond interactions, the more electron density is being pulled off of this phosphorus. And this is kind of what we'd expect, because the electrons on this oxygen are being involved in hydrogen bonds, and they're being pulled physically away from this phosphorus. Now, what happens if we do this exact same experiment with a flexible Lewis pair? We find that the pattern actually reverses. Now, the more hydrogen bond donating the solvent is, the more shielded the phosphorus is, the more electron density is actually found on the phosphorus. So we see exactly the reverse pattern. And the reason has to do with this interaction with the boron. What we find is that if there are no hydrogen bonds for it to compete with, it is more available to sort of interact chemically with this boron. So we can see this plotted very badly against each other. We can actually see the phosphorus NMR shifts. And on the bottom, we have the kind of control. And as we decrease the hydrogen bond donating strength of the solvent, we see that the chemical shift goes down, meaning that there is more electron density located on the phosphorus. The opposite is true of the flexible Lewis pair. Where the more we decrease the hydrogen bond donating strength, the more free the phosphorus oxygen double bond is to participate in this intramolecular bond. We can also see evidence that there is some kind of structural change going on in UV vis. UV visible light, I'm not going to explain the method too carefully, but because I think most of you are probably already familiar with it. But essentially what we see is that this absorbs at different wavelengths, quite significantly different wavelengths, depending on what solvent we are in. And this indicates that there is some kind of electronic change occurring within the molecule, because the position of the relative positions of the filled and unfilled orbitals must be changing in order to change this absorption energy. So what they found from computational modeling of this was that in this sort of simple flexible Lewis pair molecule, the lowest unoccupied molecular orbital in the closed form was spread across this bithiophenol backbone. However, in the open form, it is concentrated directly on this boron. And this is actually kind of what we would expect, because we expect Lewis acids, such as borons, to have unoccupied molecular orbitals, which are relatively low energy and can therefore interact with Lewis bases. So this is pretty cool, but the Arsenal group decided to ask themselves, what would happen if we functionalized this to a platinum? Would we see different kinds of electronic changes between the closed and the open form? So they decided to synthesize this thing. So we can see over here on the right, we have this exact same motif of the flexible Lewis pair. But on the left, what we have is a platinum center. And this is the part that I thought looked pretty similar to a hydrogen evolution catalyst. And what we see is that the actual electronic changes are somewhat different. We don't actually see a difference in where the LUMO and the HOMO are located on the molecule. They are located in the same position, but that doesn't mean that there is no electronic change, as I will get into later. So the first thing the Arsenal group asked themselves was, is this actually a flexible Lewis pair? Does it work? And the answer is yes. They observed in Phosphorus Nmr the exact same pattern, where the more hydrogen bond donating the solvent was, the more it lay over to the right, which is the more shielded side of this spectrum. And this indicates that as the hydrogen bond donating capacity goes down, we are seeing more interaction in this closed form. However, when they took a UV-Vis spectrum of this, they saw some very interesting results. So instead of the very large change that we saw in the previous UV-Vis spectrum, they instead saw a relatively subtle change. There is a difference between these two peaks, but it's much smaller. And this indicates that we may not be seeing quite as radical of changes in the HOMO and the LUMO of this molecule, which is pretty exciting, because it means that instead of totally changing the chemical function of this molecule, we might be sort of getting very subtle changes in reactivity. The other thing I'd like to mention that's pretty cool about this is that by functionalizing it to the platinum, they increased sort of the length of the conjugated chain, and they conjugated it to a transition metal, which means that the wavelength of absorption actually moved into the visible light spectrum, and as well as fluorescence, which I didn't show the fluorescence data here, but they tend to be very close together. And the result of that is that they show very pretty colors when you make them fluoresce under a UV light, which is pretty cool. And also, so these are all solutions of the exact same thing in different solvents, but we can actually visually see the difference in the energy at which it is fluorescing. So what is the underlying cause of the electronic change that causes the change in the relative position of the HOMO and the LUMO? And the answer is that when you change the conformation of this molecule, when you change from the closed form to the open form, you are changing the angle between these sulfurs along this bond. So as they found out from computational modeling, in the closed form, the angle across this bond tends to be about 22 degrees. Whereas in the open form, it is much freer to rotate around this bond. And this means that it will tend to form a conformation in which there is less steric interference between these bulky groups on the phosphorus and these bulky groups on the boron. So in effect, this bond becomes a kind of molecular switch. So what we see is that in the closed form, there is a connection in conjugated bonds directly from the platinum all the way across this molecule. There are alternating double or triple bonds all the way across. And this is very important, as those of you in organic chemistry will note, because it forms these very large conjugated systems. Whereas in the open form, it is actually broken at this bond. The conjugation becomes much weaker across this bithiophenol backbone, and the conjugated system is much smaller. This indicates a chemical change, an actual electronic change that will affect how much electron density is located at this platinum. And as I already mentioned, also from computational modeling, they found that the LUMO and the HOMO of this did not move. So the LUMO was in the same position in both cases. This indicates that maybe we can actually very subtly change how much electron density is on the platinum, depending on which conformation this is in. And this is very, very exciting because it could give us new insight into how, if this involves hydrogen, it could give us new insight into how the electron density on the platinum actually affects the hydrogen evolution reaction. And we could actually change which form this is in and see which one actually evolves hydrogen faster. So now I'd like to get into the actual synthesis I performed. So I'm going to walk you through this synthesis step by step from the very beginning. So this reaction is very familiar to those of you who have taken organic. It is what is called a Sonogashira reaction, and it uses palladium and copper co-catalysts and a base, and it essentially couples this on to this bromine position. And the Arsenault group found that this bromine position was selected for, somewhat unsurprisingly, because this is a very large, bulky catalyst. And this position is somewhat more sterically hindered from the other the rest of the bithiophenol backbone. So this reaction I did in the lab over the summer, and it worked super well. I got like a 90% yield. It was fantastic. So then I moved on to the next step. So this is also familiar to those of you who have taken organic chemistry, I mean. And so essentially we use a strong base called N-butyllithium to lithiate at this bromine site. Or actually in this case, this bromine site. And by using one equivalent, we can selectively lithiate exactly one of these two bromines. And then we do what is effectively a nucleophilic attack on this phosphorus. And we can see that this thing attacks and it bonds to phosphorus here. Unfortunately, when I actually did this over the summer, this reaction didn't work very well, and I got totally stuck at this step. But I'm going to walk you through the rest of the synthesis and then come back and explain why I think this didn't work. So the next step of the reaction is actually very, very similar. We lithiate the other bromine site, and we do a nucleophilic attack on this bromine reagent. From there, we have to oxidize the phosphorus in order to get the phosphorus-oxygen double bond that was so important in our flexible Lewis pair. And to do that, we just use hydrogen peroxide, which is familiar to most of you as a household chemical. From there, we use a reaction called TBAF, which is essentially used as a source of fluoride ions in an organic reagent, or in an organic solvent, excuse me. And this deprotects one of these two alkynes. And what the Arsenault group actually found that was somewhat interesting was that it selectively deprotected on the phosphorus side of this molecule. And this is pretty cool because it means that we can get the same product every time we run this reaction. From there, we use a copper coupling reaction, which is actually very similar to the Sonogashira reaction we saw before. But in this case, we use this platinum reagent, which is consumed stoichiometrically. And we are able to couple this alkyne here to this platinum center. And we get our final Arsenault product that I am hoping will evolve hydrogen in a hydrogen evolution reaction. So what went wrong? Basically, I ran this reaction a whole lot of times this summer. It's a very scary reaction to run because a lot of things can catch fire. And every time I ran it, it didn't work. I didn't see any of the actual product that I was hoping to get. So what was going wrong? The big problem was with this reagent, which is called chlorodiphenylphosphine. So the big problem, there are several problems with chlorodiphenylphosphine, but the big problem that I was having is that it's very hygroscopic, which means that if you expose it to air, it will actually draw water out of the atmosphere because it has such a high affinity for water. So the reaction that I would like to happen when this is going on is I would like my lithiated intermediate to do a nucleophilic attack on this chlorodiphenylphosphine and form this bond to the phosphorus here. What actually happened when water gets involved is that instead of reacting in a nucleophilic attack here, it is simply protonated and gives me this useless molecule which does not contain the phosphorus that I need in order to make my flexible Lewis pair. There are a whole bunch of other problems with chlorodiphenylphosphine that I wanted to avoid. It's kind of expensive. It's dangerous. As it turns out, it can dimerize to release chlorine gas, which is not something you really want to be doing in the laboratory. And it can also catch fire on contact with water. It's very difficult to handle and work with. So I started looking for what other reactions can I use to complete this step. So I found this kind of cool reaction in which aryl or vinyl halides can react with this diphenylphosphine oxide. This reagent is a nice white powder. It's much less sensitive than chlorodiphenylphosphine and much less likely to catch on fire if you spill it on the bench. By running it through this copper coupling reaction, using this TMEDA as a ligand for the copper and some kind of base, which ultimately is used to consume this proton, we can actually get a link. We can couple this aryl group onto this basic phosphine oxide backbone. And in this paper, they managed to get really good yields for this reaction for a very wide variety of substrates. So my question was, I have something that looks like a halide, which is attached to this conjugated system. It could be very similar to an aryl or a vinyl halide in terms of its sort of electronics. And my question was, if I ran this through this reaction, would it work? So why did I choose this reaction? What did I think would be very useful about this? So the big thing is that the reagents are cheaper. They're also much less dangerous, as I mentioned. This white powder is relatively non-reactive if you just leave it out on a bench, especially compared to chlorodiphenylphosphine. This made it also much easier to handle. I didn't have to, yes, I was not as worried about everything catching fire and exploding. The other thing is that 3 of the reagents in this, copper iodide, potassium carbonate, and TMEDA, are already widely available in any stockroom. So this would make this reaction much more accessible. And finally, copper 1 iodide is already used in 2 other steps of this synthesis. So it would be very cool if I could use a series of copper coupling reactions with different reagents to form my whole product just about. So I thought this would be a very exciting way of doing this. So I ran the reaction, I put it all in a pot, I refluxed it in toluene for 24 hours, and nothing happened. I didn't make any of what I was trying to make. So this may sound like a failure to you, but I was actually pretty exciting that nothing happened because I was able to recover the product from my first reaction, which I had already put time and effort into making. So instead of sort of destroying more and more of my product, I just managed to do nothing, which is nice because it's a little bit less expensive and time consuming for the next time I try to run this reaction. So I am very interested in continuing trying different copper coupling reactions, coppering reactions, that's exciting, but with specifically different ligands and bases to see if slightly different conditions can make this reaction work. So what are the next steps of this project? What still needs to be done? So first of all, we need to finish the synthesis. Before we can get any further with this, we have to have something we can kind of characterize and experiment on. And so in order to get over this sort of hurdle of coupling the phosphine oxide onto the bithiophenene backbone, I'm interested in exploring more variations on copper coupling methods because I think, as I mentioned, this would be better in the long run. Once I have made this, I would like to do further characterization experiments using Phosphorus Nmr and UV-Vis. Specifically, one thing I am wondering about is how many equivalents of a hydrogen bond donating solvent does it actually take to get the majority of our flexible Lewis pair into a open form. So one thing I would like to do is do lots of experiments in which I ran very slightly different concentrations of hydrogen bond donating solvent in phosphorus NMR. I would like to, of course, test this arsenal product for use as a hydrogen evolution catalyst and see if it works. And in addition to this, I would like to see if putting it in the open or the closed formation affects the rate at which hydrogen is evolved. And then finally, using this new electronic information about hydrogen evolution catalysis, I would like to propose new designs for more efficient catalysts. Now, I don't know that the catalysts, the hydrogen evolution catalysts of the future will contain flexible Lewis pairs. I actually think that's quite unlikely. But by being able to make these direct electronic comparisons between the open and closed forms, we can gain insight into the mechanism of the hydrogen evolution reaction and propose new catalysts. And ultimately, of course, the goal is to save the Earth. We are in one global crisis right now, but there is another one not far on the horizon. Global warming is on the rise, and we need to find alternatives to fossil fuels. And I, for one, believe that hydrogen is one of our more promising alternatives, and that scaling up hydrogen production will ultimately help us combat global warming. I'd like to acknowledge a few people. First of all, I would like to acknowledge my amazing advisor who coached me through this summer and a lot of failed reactions and helped me interpret everything and walked me through me getting back into organic synthesis, which was quite a process, I will say. I'd like to thank DMART for his amazing work in the stockroom. I came to him with lots of questions, and he helped me so much through a lot of things. I'd like to thank the entire LU chemistry faculty so much for this amazing journey over the last 5 years. I've learned so much, and I'm so incredibly grateful to you all. And I'd like to thank all of you for listening to my talk. Here are my references, and I'm happy to take any questions.
All right, I have a question.
Yes.
So after your whole journey through proposal and into into actually trying to attempt the work, did you learn any lessons about how to make a good proposal?
I think yes, I think so. I think I didn't realize, I guess I hadn't done any really complicated syntheses beyond what we'd done in the organic lab and the inorganic lab, of course, by the time that I made this proposal. And to me, 5-step syntheses sounded like a short, easy process, but it turns out one step can make your life absolute hell if it doesn't go right. So I think not underestimating the complexity of what you're trying to do, even if it looks simple on paper, I think is very important.
That's an important point, and I have learned that lesson myself as well.
Yeah.
Well, I hate to be kind of pushy here. I think I would love to have more time to ask questions, but I think with our little technical difficulty, we are actually at time. And as we have another talk here at noon, I just got an email from the presenter being like, I can't get in. So I'm actually going to cut off questions so we can move over there. And if you would like, thank you so much, Nick. It was a great presentation.
Thank you.
Congratulations.
Hopefully I can see you at the other talk as well. Are we good?
Thanks, Nick. Great job.
Thank you.
Sorry, Nick, that I'm running away on you.
No, that's okay.
Great job.